Okay.
So rivers are obviously probably the most important boundary condition we have. And they do quite a bit in the model, obviously, because groundwater has to go somewhere. And so they obviously constrain a lot of things, and we have to have them in the model. So I wanted to go through kind of how I had done it in the past, right or wrong, how we've done it, and where we need to go. So when I put together the Kane model, we didn't have LiDAR data, for one thing, it just didn't exist. And so like the Muhammad, we need to have all the rivers in there. And when we went from basically 2D models to 3D models, Dave, I can't do that. Oh, geez. Got something in my gut. Camera's there. I'll put it here. And so when we started modeling all the way to the land surface, then we got to be much more accurate with our rivers. It's just a 2D model, and you can put the rivers in there, and it doesn't matter so much. But for 3D, multi-layer model, yes. And so in Kane County, there's a wide variety of rivers. There's the Fox River that comes through, and then there's a bunch of small tributaries to it. One of them is fairly substantial, Blackberry Creek. Some of them flow off to the west, away from the Fox River towards the Kishwaukee. And then the model went into DuPage County, so the DuPage River was in there. And you can see by this map here, it had a lot of chicken scratch on the river. So how I put the rivers in, well, let's talk about a river cell. Well, I'll tell you how to put the rivers in first, I guess. So you can get a DEM of the land surface, but the DEM, in this case, I think the best we have is a 10 meter or maybe a 30 meter. It doesn't hit the low spots. So if you go up Mill Creek, for example, the 30 meter DEM may pick out one stream, but then the next cell it might pick up the bank. And so your river might be 10 feet higher, and then you go to the next cell, and you might pick up the channel again, and then you might go back down 10 feet. So your river profile was going like that. And so
yeah, if you drop the NHD on a DEM, the NHD does not always intersect with the river.
Sure.
And NHD plus, same thing.
And that's what you were talking about when I read that Montana report, where I had that issue of the lines not matching up with what their base map was showing.
Exactly.
Exactly. Yeah, so this is our river, and these are our river cells. The DEM is coming in and hitting, might hit it there if you're lucky, but most of the time it's not going to hit that. That's a real problem in Illinois because a lot of our streams are channelized, where they took a backhoe and dug them down 10 feet. Even over in Flatville, Illinois, you think, oh, flat DEM will work, but they came in with a backhoe and dug the channel down 15 feet, which really changes your model. So if you just take the values off the DEM, again, your profile of your river might go, something like this. And that can be a problem because, the model's calculating head in these cells. So if you get this undulation, you often get cells, you'll get flow the wrong direction.
Mm-hmm.
And so, you might have a cell, if this one's lower than this one, you're going to have flow back this way, and you'll have this whole whole lot of extra flow in your river budget. So if you look at your flow in the model and you have your ins and your outs, if you have a lot of it going on like that, and you know it's a discharging stream, you know, you might get a huge number here, like 1,000 and 2,000, say, you know, when really what you want in your flow budget is 0 and 1,000. So you have all this extra flow going between boundary conditions that aren't assigned right. So it gets confused, or it thinks, oh, well, yeah, because it doesn't know that the river has to be going downhill. So,
and there is a more advanced package for the river package called the SFR package, stream flow routing, and it does want to know that everything is going downhill, and that will not work if it tries to send water up gradient. So that undulation will just create a numeric error in that package.
Okay.
But the nice thing about that package, if you get your streams monotonically decreasing, you will always see the cumulative stream flow in each of them. So there's an advantage to it, but yeah, it's difficult to get that situation.
yeah, so the other thing with, not only do you want the elevation to be right, you know, and the river, and so you want these all to be lows, so you're not getting this funky flow back from the river. But then you're also, if you have,
Trash can.
we'll go purple today, okay? Hey, it works.
Permanent though.
There's no eraser.
I can fix that.
I spilled it.
So your model might look like this or something, right? Where you have, you know, your different model layers, and if this is where your river is, if you don't have the elevation right, you know, your boundary condition can be way up here, you know, and so if you're 10 feet too high, then it can be wrong. But you could also have cases where your river falls down here, you know, in below the top of layer 1, especially if these layers are really thin and only 1 foot thick or something, then oftentimes you'll have, in the Joliet model is a good one, or the McHenry County model, where you have a lot of rivers in the second and third layers because the stop laughing. The elevation was too coarse, and the grid elevations or the river elevations were kind of done differently. So if you have a river down here, you know, the cells above it automatically go dry, and you're creating this dry situation that you know, propagates through and just causes endless numerical slowdown. Likewise, you don't want it, because then you'll get a lot of flooding. It'll look like, if you turn flooding on in your model, it looks like you have flooding all the time. So what I always did was make sure my river elevation and the top elevation of the cell were always the same. And so there was a couple tricks to do that in the old program, and I don't know how easy it is now. But that way, what I like to see, because I'm a geologist, I like to see things in cross section that make sense. So if you have your river down here in layer 2, you know, you want to see that cross section, or if you display that cross section to somebody else, you want to see the river, you know, in the top layer at the bottom of a valley, You know, you don't want to see it over here or over here, which sometimes that happens. Well, it happens a lot with the NHD data, which we'll get to. You know, you'll show that to somebody and they go, well, that's, you know, that's horseshit. You know, you don't want the layer in the wrong spot. So the only way that, at least in the past, we've had to do this is manually. Manually put in the rivers, then copy those river elevations into the land surface file, and then make sure those cells were 10 feet thick. And there's a whole lot of steps into doing it. We'll get to why the top layer is always 10 feet thick later when we talk about drains, I guess. But the short of it is, I made the top 10 feet what I call the soil zone. So yesterday we were out and we saw that weathered zone in the core. Definitely missed it. You missed it. But so we know that upper 10 feet is more permeable than the till below, and so water is getting through that, but probably not getting down into the gray clay. So there's all kind of this mini flow system in the upper 10 feet. And so all our boundary conditions, our drains and other stuff are in that top layer, because that's where the egg drains are. You know, and then you don't want those boundary conditions in the till, because they won't do anything because the till's a little permeable. But so anyway, so we have this 10-foot soil to represent that brown horizon we saw yesterday. And so it just makes the model a whole lot more stable, at least in my experience, if you had all the boundary conditions in a thicker layer that was consistent and then didn't pinch out or didn't do any sort of crazy things. But that's something that you can do in mass later. But as far as the surface elevation, so all the other surface elevations are from the DEM, but where the streams are, where the boundary conditions are. The most important thing in that 600 by 600 or whatever square mile grid size area you're using is the river elevation. You know, you don't really care about, the model doesn't care about the land surface elevation. It's really, it doesn't, it only factors in unconfined storage and things like that. But in your model, only the top elevation of the land surface is the only one that actually gets put into the model, because everything else is done by the bottom. So if you look through the MODFLOW arrays, there's the top of layer 1, and then the bottom array for every layer.
So when you say river elevation, you mean top of the water surface or bottom of the channel? Or sorry,
top of the water surface.
Okay.
So what I would do, so this is, I had a set of clock maps for all the model areas. And so, you know, so I would look at these streams. So there's a couple things on here, but you can see the elevations are circled. So I got the elevations for the stream from the quad maps. I just said, okay, whatever's on the quad map is gospel, and that's what we're going to go with as far as the elevation. So on a bunch of these maps, you will see a circle around every contour. Actually, this is my set of maps I use. But you know, you'll see I've gone through and manually circled all of the every time a contour line crosses a stream, and that's extremely tedious. And then what I would do, now this is from the model, but is I print out the grid with the, I print out the grid with the you know, GIS file for the rivers. And this is just whatever I had. I don't know if it's NHD or what it is. And then I'd write these elevations on here, you know, 490. And then in Vistas, you could assign a polyline boundary condition. Daniel's got something else up there now. But anyway, so you would go, yeah, you'd click on this and click on that. And then you know, you could say the beginning of the line is 480, click, 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 bottom of the line, or end of the line is 490, and then it would interpolate in between those.
Is that effectively allowing you to do the river by segments or do?
Yeah, so the rivers are all kind of basically done in these, you know, 10-foot segments. So this is, you know, 700, 710.
10 feet by elevation.
You know, sometimes if it looked like it was equal distance to the same number of cells,
Yeah, sure.
I'd do 700 to 720 or whatever. But, you know, say this is, each of these are 10 cells and 10 cells. Yeah, then click, 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 click. Just follow that line and assign them. So then I have those river cells assigned. So say this comes out to be 705. Then I go back and edit the land surface. No, I could spit out the surface elevations for those points and then use that to obliterate those points in the land surface file and then add them in. So you can do that electronically. So the elevation for this cell, the river condition is 705, and then the land surface elevation was also 705. It kind of changed. It got a little more efficient with software and time as things went on. So, you know, you want your land surface to be 705. You want it to be whatever this is, 715. And then things look correct in cross section. It really bothers me when they're not correct in cross section and you don't know what's going on.
You've never had an instance where you interpolate between those 2 points, you would assign a value that's higher than the land surface?
No, I wouldn't worry about the land surface first. I do the rivers first based on these maps. And then whatever that surface elevation came to be. You know, the DEM can have errors in it.
Yeah.
The DuPage County one is really bad. It made lots of little volcanoes, or there was whoever hand digitizes the USGS didn't count right. So, like, I had a 20-foot error in Downers Grove well number 12 because it was on top of a hill, but they made it into a volcano because they didn't count up the last contour. They counted down, made it a closed depression, you know, and so everything was 20 feet off. I'm like, what the fuck? You know, it just kept coming out 20 feet wrong. And then I realized the DEM was wrong. But now the LiDAR, yeah, I mean, certainly the LiDAR is a lot more accurate.
But not when you throw the NHD over it.
Yeah. Okay. Well, let's wait to get to that.
So if you wanted to go into a LiDAR and say, here's a point, here's a point, and trace the line, you can do that. And it's, in theory, more accurate, although there's some voodoo flattening. And I apologize. I wanted to bring up the Evansville model that Hank has.
Oh.
Because it has the topo in the background.
Oh.
And that's one of the things that I don't have the example up, but I'm going to go to his documentation. So if you're just wondering what I'm doing over here, I think it's a nice.
So, got all that done.
Did you want me to show how to add in the the river string?
Polyline in.
Yeah, so imagine that you.
Before you do that, Daniel, could you share that screen? I'm sorry to think about that. Just that drop down menu and then screen 2, share monitor 2. Yeah, click that.
What's the difference between that and clean?
Clean removes the taskbar at the bottom.
Okay.
So it makes no
clean
difference.
So imagine you had a backdrop on here. One of the things that you can do, if after you get it georeferences, you can put up the topo map as a backdrop, so that you can actually go in and see, okay, there's where my contour crosses my river, and then you can, after you select river, then add your line in. So just imagine we have that in the background here. There's your 300 foot, I don't know, it's pretty low. And then here's where your next one crosses over. and then you would end at that point and put in the beginning information. Let's say 500. River bottom elevation, which
We always just use 3 feet. And
Yep.
we discuss that.
yep. I'd have to go into the math and remind myself what that does. And then some conductance value. So you heard it there, but they just wasted their time when they put it in. It doesn't do anything.
Oh,
So I don't know what it does. It's practically
know.
nothing. You can assign a width, you can assign a length, or you can just assign a, will it automatically assign a length here?
No.
I don't think it will. So a lot of times we just go in and put in a conductance.
yeah.
Right, because conductance is just conductivity times width times length.
Yeah, so yeah, thank you. We put in a hydraulic conductivity so that you get a conductance calculated there. And that the conductance is all that goes into MODFLOW's calculation.
Module manual water. Module manual water. No. It's a thing with duct tape on it.
Oh, would it be on this back? Or
Yeah, it would be on that.
This
side. Yeah. It's a thick USGS report.
But that conductance, you can think of it as the resistance to flow between the aquifer and the stream stage. And so it goes in that calculation to determine how much exchange happens.
And permeability of the stream bed.
Yeah, yeah, it's the thickness of the stream bed. That's the thickness of river bed. Stream bed, sure. The hydraulic conductivity is the vertical hydraulic conductivity in that thickness, the one that's defining the resistance, and then the width and the length. And you click OK, and then you have to put in the end. So let's say that was 450. Just go 3 feet below.
If you did different connectivities, it would interpolate those along the line.
I believe so. Let's check.
Yes.
And then we'll just go OK. So here, all of this should be in layer 1. A lot of times I say no. And there's your stream. And so you go in, and yeah, we start at actually 499.23.
It'll tell you down here what the conductance and the head are.
Yeah, and yeah, it's interpolating that to be a lower, which of course doesn't make any sense, but yeah, it's interpolating it to lower as it goes along in this case.
Well,
Could you pass it?
yeah, there could be.
Material?
Or maybe there's a dam there and you're getting more and more silt falling out along that reach, so you're actively decoupling.
Sure.
So, I don't know.
So we have, if you have the backdrop, you can imagine there's gonna be a lot of clicking.
Yeah.
And there's DEMs, there's NHDs. So the theory is we want to try to move away. We're building a statewide model. We're building a transient model where these are changing through time. So what do those values mean?
This is a one-time snapshot. This doesn't give us
Yeah.
any temporal.
And what is that snapshot?
Yeah,
And
that's a good question.
I don't know if that's something that,
Well, yeah, and you know, we have accurate, this is a lot like Q710 data, but we have accurate information where the gauge is or whatever, but do we have accurate elevations away from those points? And so the LiDAR, well, LiDAR doesn't see water, right?
right?
Well, there's different kinds of LiDAR, I guess.
Yeah.
Green LiDAR sees LiDAR.
Yeah, but I think in
it
principle, you're
sees the
right.
bank until it gets to stops getting any reflection,
Mm-hmm.
and then you assume that last bank elevation is it. But a major problem with LiDAR for us is they're always flown in the spring because they want the leaves off the trees and something else. So the LiDARs are all flown in the spring when all the water levels could be much higher
Yeah,
in the streams.
yeah.
You know, they've gotten a lot better at field verifying them. The early LiDARs were notoriously error prone as far as elevations go. But Yeah, so there's problems with DMs and there's problems with LiDAR. So let's get back to that. So, I put all those in the model, and then so there's a bunch of decisions to be made. But first, I kind of error check it, and this is basically a 2D model of Kane County, which has 17 layers or something. But this is running a model with just the rivers, no recharge, no pumpage, no anything. So I do this error check to make sure all the streams go downhill. You know, and I didn't screw up somewhere, and obviously I did this after I error checked it because I probably had errors.
It's fine. Or you can push the pause button as you switch around, and like the double, and that just stops.
This one?
Yep. And then you can basically, yeah, that'd be great if you could show that from the screen.
So, yeah, so, you know, you just by doing this, and this is something you need to be careful with modeling, is, you know, you do mimic what you're trying to model pretty well just by the boundary conditions.
Mm-hmm.
You know, so your boundary conditions are going to
You can
control a lot of things, and a model with too many boundary conditions is so well constrained that, you know, nothing happens. But then when you add all the geology in and all the layers and all that kind of stuff, it gets confusing. We talked about conductance. So this is a map of the geology, the first layer of the Kane model. And so you can, so where it's riding over yellow, it's riding over sand, where the streams are riding over the olive color, it's over clay. So we can assign our conductance that way. So I think in this model, I used a high one for sand and a low one for clay. What I found though was it's insensitive in many respects to conductivity if the stream is discharging. So if we have, you know, water, and this is our river cell, and say this is all low permeable stuff, and you have flow going, now it's going to discharge here. What the conductance does is basically provide a resistance. So the conductance is acting as, in the conceptual diagram here, in the book, it's adding a low permeable material. So so I mean, is a stream bed riding over till going to have a significantly lower conductivity than the till itself? Probably not, or the soil. So, what I can say. So you can actually raise this number to infinity and it doesn't do anything.
The conductance value?
Yeah. It does. It's not that sensitive because the flow is controlled by the fairly low K. I mean, it might change a little bit, but even in the sandy, if this is all a sand.
Oh, I see. Yeah.
You know, and the sand is trying to get out. It's trying to get out here too. You know, it's going to try to raise the head in the cell to force it through there. But you also have a high conductance, and you have this river elevation set. You know, if the conductivity of that cell is high enough, you never really build up a head difference. And so putting in a low permeable material for a discharging stream, I've found to be completely insensitive.
When you say discharging stream, you mean a gaining stream?
A gaining stream, yeah.
Okay.
Sorry.
No. Sorry.
And so, you know, and then also in our experience, like we've seen the sand boils out in Mason County, you know, if you get too much head across that low permeable bed, makes it buoyant, and you get sand boils, and you'll get a good interconnection. If a storm comes along, you know, it's going to cut down into that, and you'll have holes in the low permeable material. So for most of the model area, the river conductance just didn't matter. But so usually I just set it at a high value and don't worry about it. But then where it really comes important is in the losing streams. So, you know, in Kane County, you know, we had Mill Creek, for example, that was losing water. So if you have a really high conductance here, you're going to just dump water in, whatever it'll take. But that's often not the case. So, you know, if you have a production well over here and you have a really high conductance for this river cell, it's just going to suck as much water as it needs to. And that might not be what's going on. So if you have low permeable material here, you know, then your drawdown, for example, can go out underneath that or something, and you don't get as much water. So this I kind of really view as a calibration site, or a site-by-site calibration thing. So in Mill Creek, for example, what Mill Creek does is, well, you get Blackberry Creek. So this is the Fox coming down, and Blackberry Creek is up here. It's right by Jerry Elliott's house. And so I draw a cross section. Blackberry Creek is kind of up here, and then the Fox is down here. And this is just the natural elevation. So the Blackberry Creek is actually losing water because the head is so much lower in the Fox. And that's been documented in some of the Q710 measurements and stuff. So, you know, how much Blackberry loses is dependent upon the conductance term that you use. So, another example is the Sangamon River out in Monticello, here west of town, for the Muhammad Aquifer. If you assume that there's a good interconnection, it loses too much water, and our drawdown, especially like for Decatur and stuff, is way off. And so that's why we did that giant test out there in 2003. And, you know, we needed to put in a low conductance, not something lower than the sand, to prevent too much water from coming in, because we did have some drawdown spread out underneath it. We know a lot more about the system now, but at the time, we needed to do that. And that was just, a calibration thing to see what works. But we need to learn from these examples where we have wells from the stream to assign this to areas that we don't know. So if we're go to someplace in McHenry County and someone wants to put in a well, you ask, well, how much water is going to leak out of the river? If you assume that there's no low permeable material, you're going to get a really high number. But if you assume there's something there, it's what inhibiting flow going down, then you're going to get, you know, more drawdown or something different. So, that's where it becomes a lot more important.
May I ask you something?
Yeah.
Classic issue when you're first developing a model is that, let's say this is your second order stream or what have you, third order down here, is that you will see contours like this, where water is mounding up and being added. And when you do a mass balance, this is a rather enormous amount of water that you know a second order stream couldn't actually put in. So this is one of the first things to check if your resistance is at least reasonable. It's not, you don't have enough resistance if you start to see these big mounts.
Yeah.
But it's very, very common to see models this way, where people just, okay, they got a calibration, their their calibration is down here, and they're not really looking up here. So that's a very common thing. And George mentioned the conductance, and if it's so high, it basically approaches the constant head cell, which is the version that does not have any resistance assigned whatsoever, basically an infinitely large resistance. But you reach a point where it doesn't matter. It's all treated as infinitely large. So
Yeah. So before we leave the subject of conductance, so this conductance is calibrated to average conditions, but our surface water folks would say, and this is something we tried to do in Henry, Illinois, is that when the flood comes, the flood, the water level jumps up, like in the case of the Illinois River or the Sangamon, it jumps up 10 feet. So that acts to suspend a lot of that stuff that was all sitting there nice and flat and low permeable. It not only, cuts through some of it, but it also suspends it. So then your conductance term under a flood could suddenly go way down or way up. And that's something we've not addressed, but I think that's something that's going on out here on the Sangamon River, because the data would all suggest, and I can go into that, but that it's not leaking under low flow conditions. It's only leaking under flooding conditions. And is that because it overtops the banks and there's some sandy area there? Is it suspending the sediment, or just because of the fact that the gradient jumps ginormously during a flood that is pushing a lot of water?
Mix of all three.
But or a mix of all three, So the conductance term I'm talking about here with what we've done is assuming that it's constant for the constant condition. But that could really change. I'm assuming it really changed in the Mississippi. You get a lot more stuff suspended and stuff. And so that'd be something to talk to the surface water folks about, or take samples out in the river during floods and stuff.
When it's super safe to be on the river.
When it's super safe, yeah.
Could you talk, we've talked a lot about conductance. Could you talk briefly about, just in vague terms, the math behind where what's that conductance calculation? What is that interacting with in a multi-layer model? So your river cell's in layer 1.
Yeah, so the way I've set it up is to have, this is a 10-foot layer. So everything is happening in layer 1. You can set a river bottom to be deeper than 10 feet, but then your river cell is kind of trying to do 2 layers at once. But like in the sketch there, it assumes that it's all in layer.
Within one layer.
Within one layer,
So I guess what I'm getting at, the flow exchange that's being calculated with that conductance is the flow exchange between the river boundary and the properties assigned to that cell in layer 1, correct? And then layer 1 has a separate calculation with the surrounding cells. So that river boundary is interacting. There's a groundwater solution within that MODFLOW cell, but then there's a river cell that's a separate calculation going on within that cell.
Yeah, so it's basically doing the same thing as a well does.
Yeah.
And you have this nice diagram here that says, okay, this is exactly what I'm modeling. I'm modeling this and there's this layer. No, what you're really modeling is the cell and then a flow turn that comes out of the middle at some kind of cube. And so it's not this nice system. So you know, the water that's coming in and out of the river is taken out of the middle of the cell. It's not, don't envision it as going out the top or out the bottom. It's coming in the middle. So everything in a MODFLOW model is done on this cubic system. There are no cells within cells that, you know, make this nice diagram look nice and pretty. So this Q is controlled by the head in the river that you assign, the head in the cell. So you're creating a gradient. You know, it'll try to calculate a cell just as it does normally, just like it does for a pumping cell. And then, you know, and that's controlled by, it's related by the conductance, you know, relates how those two. So if your conductance is high, these two will always be the same. If your conductance is low, then your Q could be something less, and your heads can be different. Not a whole lot different. I never really see them to be significantly different.
Mm-hmm.
But, you know, the bigger this difference is, the bigger that Q.
Yeah, it doesn't always take a big difference to get a big.
Yeah, so if you have, you know, something in the next cell, like a pumping well or something that's trying to pull water away and it's pulling water out of this cell just because of the flow system, you know, this is down gradient out of the well, then this tries to drop, but this is trying to keep it constant, so your Q goes up. If that makes sense. So yeah, don't think of it as a nice, pretty diagram. Just think of it like all the other boundary conditions is pulling something out of the middle. What else do we want to say about conductance? Yeah. So I generally only worry about it with losing streams.
Yeah.
But then you have to be careful if you're suddenly starting to assign new pumpage to an area where you're going to induce water. Then you might want to look at, oh, wait a second, now I got to consider, water being lost.
So maybe you can't calibrate conductance very well in pre-development as well as you can in a stress system.
Right. Right.
Which is pretty well true for anything in
Well,
the model,
pretty much
but
do anything, yeah.
So that's another, if you're ever reviewing a model or something and they're bragging about their awesome pre-development calibration and the system's heavily stressed now, don't buy it, because that's not a good calibration. So many people, and this is just common throughout modeling, I see it all the time, focus on calibrating to your steady state pre-development condition. It's hard to mess that up.
So they mean pre-agricultural development? Or?
But just pre any pumping.
Pre-landfill.
Yeah.
Pre-this. Yeah.
Yeah. So for Joliet, they call pre-development 1863 because they didn't have wells before.
Oh, so that's what the head levels are.
Yeah.
In that. Okay.
Yeah, and so there's some old, in that case, there's some old contours that were drawn,
Yes.
and somebody's gone through and picked off the elevations on the contours. So you're always calibrating to 500 feet or 550 feet, nothing in between, and you get really weird calibrating and straight lines, because that's all it can be.
Mm-hmm.
But that's a lot of times what you see with a pre-development calibration. Pre-development, what data are you actually calibrating to? Now in this case, we do have pre-development stream flow, but that's if you get talking about Bill Sam will talk about that then. But there are estimates, but they're always estimates. They're always models or some surface or something that aren't necessarily the best calibration target anyway. But you see this a lot where the focus is calibrating steady state. It's easier to calibrate steady state. That's why that is. But
you also have to consider like a lot of your confined systems in pre-development are going to be flowing. So
yeah,
again, what do you calibrate?
What is that? Well, at least you know that you want your water level to be above winter.
But how far above?
How far above? Who knows?
You didn't hear that. I saw it. I didn't need to hear it.
Okay, so first some bookkeeping in the model is, so you're gonna have these streams and these streams are gonna have flow budgets. And so you're gonna calibrate these flow budgets to something that your surface water people give you as what the flow in the river is. Or what we think is the groundwater discharge to the stream, I should say. And so for the Kane County model, I assigned each of the sub-watersheds a number. And so and I know this gets complicated, but so all the river conditions I've assigned a reach number starting with 500, and then those subsequent numbers after that for each different watershed. So what I could do with that, is make a bar chart or whatever. You have the model spit out. Will spit out the flow budget for each boundary condition, or summarize it by reach, and then that number I could compare to a number of what we think the base flow is in the stream. So that's just, so like you see, each of these will have a number like 12 is Mill Creek, 9 is Blackberry Creek. That's what those numbers are. It's just those randomly assigned watershed numbers, so I can keep track of flow budget. So then we also have drains in those conditions. So the drains will be, instead of being 507, it'll be 707 or 607 or something. So
Yes, I would.
you can easily add up things by watershed if you do your reach numbers correctly. So
then HSUs are a great way to do that.
Yeah,
Yeah,
everything you were
really
just describing made me think like,
Yeah.
oh, that's how we're working with the HSUs. Cool.
So HS.
But they're called hydrostratigraphic units in groundwater vistas, but effectively they're just zones that you can summarize easily.
Yeah, you can do a mass balance on HSU.
Yeah.
Whatever, and you can give it a number, whatever number is on
So
there.
is this kind of like breaking it down into watersheds, or just pieces of a puzzle of one watershed?
well, yeah, I don't know what HUD code those are.
Yeah. But I did a similar, or I'm doing a similar analysis for water supply planning at the county level. So each of my HSU is a county itself, and I'm able to look at what the mass balance summary within that county is. So similar kind of analysis.
Yeah. So any river cell in this, zone 8 will be in that zone 8 total that I can look at for Big Rock Creek. So in Kane County, then you have to decide what is a stream. Okay. And then, so stream flow is a continuous thing as far as the amount of flow. I mean, when a stream, unless it's getting sewage discharge or something, but if you look at what they call a flow duration curve, which is what surface water does with the ILSAM model, is all statistical. So it's flow versus percentage flow. So like a 99% flow, 99% of the time the flow is greater than X. 80% of the time it's greater than this, 50%. So if you're gauging a stream, there is no one value that says, oh, this is groundwater. Some people do base flow separation. And so what we've been doing is using what's called the Q710 value. And you'll hear it's a 7-day low flow occurrence over 10 years. So that's also the legal description, as Wes will like to talk about with the Kankakee. Like when Joliet goes to the Kankakee, they can only use so much of the Q710 flow value.
Yeah.
Or they can't, or once the stream goes below Q710,
then that's when they have to go to a backup supply. So all these runs I was scrambling around with for Jeff Freeman were all based off of the fact that IDNR changed their tune, and they said previously we were going to use Q710. Now they're saying, oh, but in the last drought, we saw impacts to the mussel population and fish assemblages and what have you. And so that's the ecological threshold. And so it changed. So this isn't always used, but I think the Kankakee River is the first exception
Oh,
to
I don't know.
Q710, but I don't know that for a fact.
Well, that rule hasn't been around that long.
The
So
Q710
there's a
rule?
lot of people grandfathered in.
Oh, yeah.
Yeah.
So there are obviously exceptions as well.
How often are these Q710s assessed? Does it just push a button and that's a Q710 as a 2019?
No. So let's talk about Q710. So this is obviously done before computers. So the way they were done is there'll be a gauging station.
Let's not worry about it. We'll discuss it later.
So let's take Person Creek, for example, or Blackberry Creek. There's a gauge on Blackberry Creek. And so they basically do the statistics and determine what the Q710 is at that gauge.
Okay.
So that's the only data point we have specifically. Now, Blackberry Creek's been studied a lot, so there's actually more gauges. But, and then everything upstream is estimated. So it is estimated to where, in a lot of cases, where it goes up to zero. So zero is where you can consider the stream to become permanent. Above that, it's intermittent. Now, that's not quite true. That's just, that we're drawing an arbitrary line on here, and the arbitrary line is a Q710 because that's what surface water has done. If they'd done a Q99 map or a Q80 map, we could use that too. But this is what they've done.
Okay. So these are, to get to your question of how often are these updated? These are updated through water supply planning, at least right now. So when we go into the Rock River region, part of that is to update the ILSAM numbers for that region. When we go to the lower Illinois, they're either updated or created for the first time. The whole state hasn't been done. But that's the idea with water supply planning. Like with the groundwater flow model.
Q710 for the whole state, the ILSAM model. So the ILSAM is the Illinois Stream Flow Assessment Model. That's basically a spreadsheet model that VernNap created that creates the statistics for any stream in here based on the gauge data and then extrapolation.
The Q710's been done for the whole state?
Yeah, these are done for the whole state.
Is it the one?
But the ILSAM model has not been done for the whole state.
And ILSAM is used to update these numbers.
Yes.
Yeah. Okay. I guess I wasn't aware of that because that's not been digitized. Only ILSAM results have been digitized.
Oh, see, that's why I keep asking for a GIS coverage of this.
I don't believe so. My understanding and what I've seen is that it's an incomplete coverage of the state. That's where I was confused because we have some
in
of
my
those
office,
digitized.
I have a stack of these, and they're all from different dates because Vern has updated. This is Bulletin 57, which came out in 1973.
Okay.
That did the whole state.
Okay.
But like the Northeast Illinois Region 2 map has been updated several times since then. So you have to know what the latest copy is. And I don't necessarily know that.
I don't know if our digitized version is the latest copy either.
Who would know that? Vern?
Vern, probably, maybe Jason. It got very confusing. But no, Vern's like, oh, you want to use this one. They also have ones for the harmonic mean, which are more like the Q50, I guess.
Yeah. He has a lot of statistics. He does a lot more with ILSAM than just Q710.
Sure.
There's some 70 flow statistics that he calculates.
Yeah, Q20, Q50.
Well,
But the Q710 just seems to be the magic low flow number. So obviously the streams will go below the Q710, but is that, groundwater could be evaporating. It could be, what you call the groundwater contribution is probably best represented by the Q710 or some similar statistic in that range. on a steady state basis. But you could certainly have
Yeah, maybe.
maybe, and that's, well, before we get into that discussion. Because we need to move away from that.
Yes.
Let me continue with what we did before we start what we need to do. And so, yeah, so on these Q710 maps, so for making a model, basically I would digitize this stream and put it up in the model until the map said it was 0. So those are what I would call the permanent streams. The ones in blue here, yeah, I don't know where that blank one is. Yeah,
Whereas, are the yellow,
the ones in blue here.
match that.
So you actually notice they're different on here. And so that's because when we did the Kane County study, we actually had Q710 conditions, which is rare. And we had, well, first we had 2005, which is dry, and then 2007, we actually had Q710 conditions. So we could go out and precisely look at each stream, doing the field work, writing notes on all the quad sheets. You see there's all kinds of notes on here that, you know, the stream was flowing here, it wasn't flowing there, and then we could.
How did those match up with the previous Q710
There's
equals 0 stat?
some quite a few differences. Yeah, there was quite a few differences. Mill Creek went higher up, and I have to look at them specifically, but
Like tens of
we
miles
had
of
a lot of
differences.
issues in the urban areas. Things were very different
Sure.
in the urban areas. There's lots of different miscellaneous flows and things, and you know, when you start messing up the watershed so much with sewers and storm drains and everything else.
So what
Detention
database
basins.
is this information of observed Q710 stored in? At least you didn't do this. So
Yeah.
that's a little better.
But then, you know, this is a 1973 map. We just pulled that off the shelf. There is not one bulletin that has all the updated ones. So you have to know which ones have been updated and get those. So like the Q710 in the Fox has been increasing over time because the sewage discharge to the Fox has been increasing over time.
So the 10-year period you're looking at is the previous 10-year period, ideally?
No, it's taken over 30 years. So they go back 30 years and look at the flow for every day and plot that up and then do a frequency of flow on each of those days over the last 30 years. And so, you know, and so 90% of the time the flow in the river was over 7.5. Or the Q710 here is about 6. So every stream will have this sort of relationship.
Yeah, so I'm confused as to the
Like a
process
stream
you
rating
just
curve.
described doesn't include the numbers 7 or 20.
I was curious about that too. Like, how do you go from the percentages to 7 days in a row every 10 years? Do you happen to know?
They are not looking through the record for, it's a statistic.
Okay.
I don't think they're actually going through and looking at the hydrograph and deciding on a 7-day period. And it might always be 93% or something. I don't know. I'd have to look. You got me on that one. I don't know.
I mean, so saying that it's found statistically, it takes that as a curiosity. I'm fairly familiar with plotting, stuff like that.
I mean, they can blame things on statistics.
Right, yeah, I mean, then often valid anyway. So.
That'd be a question for Jason.
That's a great question though, because what does it actually, I mean, you get what it physically represents, or at least it's described as physically representing something, but does it it doesn't seem, I would love to know the steps where they go from the statistics to actually linking it to that physical representation. You know what I mean?
Yeah, I don't, you'd have to have Jason saying.
Yeah.
Because I don't know.
Is
Um,
ILSAM documented anywhere on our website?
No.
you can do that in
Job.
your spare time.
Yeah.
So ILSAM,
That's one of the major things that's being discussed as happening
Okay.
in the next couple of rounds of water supply planning is to get some documentation.
Yeah, how is Jason developing or updating ILSAM? I mean, it's probably worth it.
Turn the camera on.
So we're actually getting farther than I was thinking we'd get today, because I was really thinking this discussion should be in 2 sections.
Yeah.
What I wanted to get to today was, well, how we've done it in the past. And so there's a lot to get up to speed, because especially with the Q710s.
Mm-hmm.
But
As part of that, did you need to talk about drain cells?
we'll get to drain cells.
Okay.
We're still a ways from drain cells yet.
Okay.
Well, actually, you could start talking about drain cells. But the point I wanted to make is you put in these river cells based on the Q710.
Yeah.
If you go in and put a production well in right in Elbert and say where that Q710 is just starting off, from 0 and going, you might be sucking a lot more water out than this stream has in it.
Mm-hmm.
Because a river cell will supply an infinite amount of water. As long as this H is high and the cell is low, it's always going to, supply an infinite amount of water, unless you have the conductance low, or unless you've calibrated that. So with when Elburn put in some new wells right along the creek, they might be sucking a lot of creek water in when there's water in the creek, because the creek goes up quite a ways past the wells. But then when the creek goes dry, then your model is sucking out water that's not there. And so there's 2 sides of the equation to be careful of. I guess more so the other side of the extreme when you're in Q710 conditions. Yeah, you're not going to. You may have an unrealistic situation where you're pulling out way too much water than what's in the stream. So that's a hazard of river conditions. The other thing I would say before about the Q710 calculations, which is where I think we can do better, and Kane County is kind of a good case for that, because the bright yellow is the sand. So we have a lot of streams that start up where the sand bodies start. And so if you look at a creek like, some of these side creeks into the Fox, like you'll see their 0 low flows are right along this transition from clay to sand. And so, whereas another stream, even the Q710 that is displaying its pre-development can be 0 down here. I mean, the pre-development ones, so you could have a pretty big drainage area with a 0 Q710. The Fox isn't going to have a 0 Q710 because it has so much sewage discharge in it. Same way with, the Plains River. But so, if this is Blackberry Creek, we have the gauging here, we're doing our estimates of Q710 upstream, and this might stop up here where we actually observed it, or, the watershed is just small enough, there's not enough water to maintain flow. But when you start combining these Q710 ILSAM factors with the geology, then things will start to hopefully appear. Like if this is the till versus sand line down here, suddenly these streams start popping up. So Vlad was making fun of my chart here. So I was tempting to look at, well, okay, flux versus sand percentage in here, and you could see a relationship, but it wasn't all that great. But I think if we put our minds to it we can estimate at least Q710s and maybe some of the other statistics for, for surface water purposes from our groundwater model, or you can call it a groundwater model or some hybrid groundwater surface water model, where you take into account, because we'll know the slopes, we'll know the soil conditions, and we're using so much of what we use in the groundwater model now are the same inputs for ILSAM. So, and we can add flow, we can do all kinds of things, and we can add a well in the stream to put effluent in or something. So that's why I think they should be combined eventually, because it's really just duplication of effort. In some degree, if that makes sense.
Yeah.
At least for the Q710. Now, we might not be able to come up with Q90s or something very well, but we'll be calibrating to these points. So,
So the other option for dam screens, keep throwing out projects at dam.
yeah,
Yeah, we were going back and forth, fault zone or surface water, and
so the question becomes what you do with the streams above the Q710s. So above the Q710s is 0. And so because we have all this till at the surface, this map shows where the Q710s are less than 0 and we're over clay. But basically what we found that works is that we put in drain cells. The drain cells are different than river cells. In one major respect is they can only take water out. So what we're assuming is these streams, which could contribute to groundwater during higher flow, but under low flow conditions, can only accept water because they would be dry. And so you could call the whole groundwater flow model of Kane County a Q710 model, because that's kind of what we're calibrating to for our flow statistics. So it's what I might refer to as a dry model, versus if we try to calibrate to the Q50 or something, we need a lot more recharge in, to get the river flows out to generate those numbers. And we probably need a lot more lateral flow in layer 1 of the model. That's really where that flow is. Because if you think about it, if the groundwater discharge doubles, well, that means your gradient needs to double. And the gradients in our Muhammad aquifers or our sandstone aquifers aren't doubling. We know that. So
just based on what you said there, though, you're talking changing recharge without changing the stage, correct? Because the stage it's just fixed. It's whatever we pulled off. So these flow statistics, in reality, you're going to have differences in stages along with them. But when we model, it's always the same old steady state stage that we throw in.
yeah. Give me the color shade. Yeah, so if our river stage is right here, this is our river cell, this is our river stage. What happens in these cells in the urban areas and in the farm fields, there's a lot of drain tiles. So where this is clay, we've assigned a drain condition. So these cells all have drain conditions in them. They're 3 feet down. We just take the land surface and subtract 3. And so this has a head value. They don't have conductance, do they?
Yeah.
Oh, they do have conductance. Yeah, they have conductance.
Yeah, here's the properties for a drain
Oh, okay.
cell.
Yeah, see, I just make it really high. I don't worry about it.
Yeah.
Because drains can only take water out. So if the head in the cell gets above this level, it takes water out. Now,
And when you say take water out, like just obliterates that mass, right? It doesn't import it into another part of the system. It just
correct.
You can do that.
You can do that, but it
Yeah, this it's called return flow. You can actually activate this and then tell it a specific location that you would want that flow to go.
Okay.
Potentially.
Yeah.
We don't do that generally, but it's certainly possible to do that. And there's how you can define your return location.
Okay.
Here.
Okay. But in general, if you're just using a drain cell without the return flow option,
Yeah.
it just removes that mass from the system.
Exactly.
Okay.
Yeah. So you think of it this way, okay, so we're assuming that, and Jason talked about this yesterday, the water table is always close to the surface in Illinois.
Mhm.
I mean, in the clays,
Mhm.
you know, that's why the cemeteries are on sand patches. You know, the water table out of the drill site was like right at the land surface. And so the problem is, you know, to assign a recharge value, you basically have to calibrate for every cell because each cell is going to be different because the slope is different, the gradient is different. You don't know how much recharge is necessarily coming in for each cell. But so having this drain cell at the surface and having this superficial clay layer, you know, just think of that brown material we saw yesterday.
Mhm.
Only a little bit of water is coming down. So basically we add excess recharge to keep the water table at this level. And then we have this Q that comes out from the drain and we get a little bit of water going down into our flow system. So if you look at the Muhammad report, this is what I call effective recharge. So we have all these all the surface conditions, all these boundary conditions in the upper layer.
What percentage of the recharge is the effective recharge?
Okay, so this might be what, an inch a year, and this might be a quarter or a half.
Okay.
I could give you exact numbers, but
I think
and they're in the Muhammad report if you want to read it, or in the Kane report. They're both in there.
But I mean, you can assign, correct me if I'm wrong here, George, you can just keep cranking that recharge that you've assigned to drain cells up and up and up, and it's not going to influence your solution. You're just going to be draining out more water with the drains, and what's going from layer 1 to layer 2 is going to be the same. So the percentage is going to just depends on
carry on your
how off
rate.
you are with that
Yeah.
recharge.
So you can add these Qs up, but you know, so they're all assigned to reach numbers. So you know, all your drain Qs will add up, and then you can keep track of that number.
Yeah.
You know, if you vary the recharge, it will have some effect.
Yeah.
It's not big, but it'll
Yeah.
have some effect.
Mhm.
Right, I'm just talking about the clay areas right now.
Right.
Because this number is extremely hard to hit. You know, ideally, in a sand tank model, you can come up with recharge pretty easily. But, you know, this flow might be a quarter of an inch a year. If you do not have this drain cell in here, if it's not in here, if you're not exactly right on your recharge, either you'll be less than a quarter inch and this cell will go dry, and we know that's not the case because we know that shallow water table is there. Or what happens is the water table mounds up. And so you're trying to put a half an inch of water or an inch of water in something where only a quarter is going through. The model just sends the head up to 10,000 feet or something. And that creates a lot of numerical dispersion and makes your model run really increase.
So is that happening because there's no surface flow model?
Oh yeah, there's no runoff from
There's
cells.
no runoff. I mean, it won't happen in these cells, but if there's this giant spike will occur because there's not a whole lot of water coming in, but it has nowhere to go.
Yeah, but it
You know,
doesn't-
some of it will go to the adjacent cells, but generally what happens is you get this giant spike in your model.
But it only accounts for that as a head, like an anomaly within the head gradient. It doesn't actually say that this becomes then ponded water that then runs off over the slope to and feeds.
Not unless you have
No.
a drain cell there.
Yeah.
But then, you know, this flow budget can be really wacky and
Yeah,
it can
sure.
be really wacky.
Sure.
And then your model, instead of solving what it should be solving, is just trying to deal with this.
A pillar of water.
Yeah, this is always kind of a good back of the envelope calculation
Mhm.
when you're thinking of this, but you can see, well, this is mounding, so delta H is how much this mounds up,
Mhm.
and it's just inversely proportional to transmissivity. So you
Okay,
get a
that's
small
transmissivity.
transmissivity. Tiny in this, like 4 or 5 orders of magnitude, 3 orders of magnitude, whatever, smaller. This is very hard to control then, or recharge that's going to keep the mounding proper.
Mhm.
Whereas when this is a high key, you have a much wider range of recharge.
Yeah.
And you have calibration targets on top of that.
Yeah.
So this recharge value then becomes adjusted or, you know, tweaked based on what the river is putting out here and what I'm getting out of the drains. So, so if you look at this bar chart here, so here's the flow. So these flows are the rivers and drains added together. And the red is what is simulated. I don't know what series 4 is, but in this case, we decided to bracket between the Q80 and the Q710 because we have some overland flow from these drains, so it's not strictly a Q710 situation. So we wanted basically the flow in that stream to be bracketed by the Q80 and the Q50. Those are random numbers. I mean, they're on this continuum of what, you know, flow is in the stream. There's nothing magic about it. But we're saying, okay, this amount of recharge kind of gets us to the somewhat average, not average condition, but within the normal range. So if we had a recharge value when we were way up here, we know that we're just dumping way too much water on. But, and so for the whole county, I use the same recharge value for a specific type of, or for the till areas, all had the same recharge value. And so they all came bracketed within that. Now you could adjust it by watershed, you know, because there could be differences in the watershed, and that may be where, you know, somehow linking what we do with the flow statistics better would make that recharge number come out better.
Is the recharge value linked at all to precipitation or?
No,
Okay.
no. I mean, because we get 36 inches of rain, and that's something more on the order of, you know, at the most 5 inches. But out in Mason County, it's 21 inches.
Well, in Mason County though, didn't you change it based on
I changed it.
precipitation changes that you've seen?
No, on pumpage changes.
You change your recharge based on pumpage changes.
Because
Because you're
pumping
lowering the
induces
water
more
table.
recharge.
So if you lower the water table here, more of the water's going down than is running off.
But,
Precipitation in the last 50 years hasn't changed out in Mason County.
okay, but the Illinois River has gone up, and that doesn't change in the model.
It just hasn't gone up.
Illinois
Yes.
River stage?
It's just a dam system.
Um,
Damned.
No, I'll show you the Middle Illinois report. It's gone up about, it's
Oh,
gone
has
up
it?
a lot.
Oh, okay.
And I'm wondering maybe if that's why recharge had to be bumped up for calibration.
No, I was assuming that recharge was going up because of pumpage. So if you're drawing the water table down, you're increasing the vertical gradient.
But if your water table is
But
always,
it's already at 40 feet, yeah, I don't know.
yeah, then why does, that's always been my big question. If this is a constant head up here, the unsaturated zone, and then the saturated zone is well below it.
You're talking in the sandy areas.
Yeah,
Yeah,
yeah. Isn't that what you increased though?
yes.
So then,
Because the till will take care of itself because of those drain
Yeah.
cells.
you know, and heads haven't changed that much either in Mason County.
Well,
average,
I mean, if you take
non-pumping.
zero pumpage and add 1 billion gallons a day or whatever,
Yeah,
you're going to get a lot of drawdown, and we don't see that drawdown. So we know recharge has increased over time to bring the water levels back up. The specific mechanism, yeah.
yeah,
I mean, if you have these cones of depression that are recovering in the fall, that's diverting water away that would go to the streams. So that extra recharge is only occurring after the systems are turned off. But see, on an annualized basis, you have to account for that. If you're modeling it on a weekly basis, then you could do it that way. Then you wouldn't be, well, how do I want to say it? There's a transient effect there.
Yeah.
That
I guess I'm just, conceptually, I struggle with it a little bit, because if this is land surface and you get precipitation,
and
and
water table.
your water table's down here, or if it's down here,
It shouldn't matter.
why does that
Yeah.
induce more recharge?
Uh,
That's what I'm conceptually struggling with.
yeah, no, I would agree. But, I mean, there are areas of the county where water table is really close to the surface, and then it would matter.
Then it would,
But under the dunes,
under the dunes.
it shouldn't matter.
Yeah,
But yet, how are those cones when they where are the cones getting their water from when they shut the pumps off? So it might really be coming out of the rivers, but my rivers are steady state.
yeah, your rivers are steady state.
And that's probably more the problem than in Shelby's model, or if the rivers were allowed to change during the course of the year, then not only in stage, but also in flow,
Yeah,
then you wouldn't need to increase the recharge rates. That's a good point. I don't think so. You'd have to play with it.
yeah. I'll look up the the Middle Illinois report, because I think what they showed was that the Illinois stage from the 60s to current has really increased because more water is coming down from Chicago. And it's in the back of my mind, is that why recharges had to increase?
No, it's due to the pumpage, but I think it's an artifact of the steady state.
But are you mimicking that the Illinois River stage went up by adding more water? I think that's what I'm getting at.
Well, the model just has one river stage in it.
I know, but that's what I'm saying is that if you add a transient river stage, would you actually have to add more recharge transiently if the river was going up transiently? I don't know.
The pumpage in the model the problem is the pumpage in the model is distributed evenly throughout the year. And that's not what's happening.
Yeah.
So, simulating irrigation pumpage with a steady state model is just ridiculous. But, yeah. So you have to make it work, you have to have the recharge increase. But it's a transient problem. And so the recharge is because you're trying to model a transient problem with a steady state condition. But I think if you had a transient condition,
maybe you don't.
maybe you don't. Because then, because in a steady state, you have some sort of equilibrium with the wells and the rivers. But then if you go to a transient, then the wells kick on, they suck more water out of the streams. Because they suddenly put a gradient between the well and the streams that wasn't there before. Then when
okay.
you shut the pumps off.
So this isn't aerial recharge that you're trying to capture. It's actually induced recharge from streams.
Yeah, it's
that you
both.
miss because your model never gets enough of a gradient to induce it in the first place because you've smeared
the gradient's out. Not changing in the model. Is the problem.
I gotcha.
Well, it's changing from year to year, but it's not changing throughout the year.
So it's not. It's not this that's increasing as much as it's that.
Yes.
That's
changing.
That's the higher versus this, which is more average.
Yes.
Gotcha.
But I can't, because it's not a transient model, I can't do anything about that.
Gotcha. And you're just smearing it out then?
Yeah.
Okay. That makes sense.
I didn't say it's the best way to do it.
No, but I think it's a good discussion because it's.
Yeah, I mean, what I was trying to do is model 70 years of the growth of the irrigation. So do you have, how many time steps do you want? How many time steps do you need?
Yeah. So
and if you plot it up, so I plot recharge increasing over time, but really that could also be less discharge to stream or more influx from the stream.
Here's the plot I was thinking of then. That shows this increase in stream flow. This is at Kingston Mine. It's a little north of Mason County.
Yeah.
But around the 60s, the stream flow anyway jumped. I mean, it almost doubled. Well, not doubled, but maybe increased 50%.
Stream flow in inches, what does that mean?
The flow volume is more.
Yeah, it's
drainage area.
Okay.
Yeah.
Okay.
But like you said, the precipitation, you're right, it's not really changed. But this was explained as being Chicago.
Yeah.
I mean, this is when we had all the growth in demands in Chicago anyway, the big boom.
Okay, so the short answer is no, I did not. That's not the way I conceptualized it.
Okay. But I think this is probably playing some role
It could.
in needing to, because at the end of the day, you did it for calibration, right?
That's why. Yeah. I mean, there was no other way. I couldn't use the same recharge rate in 1950 and 2005.
Yeah.
It just wouldn't work.
Yeah. So.
Because there's been no change in long-term change in net out there.
Yeah. So I'd really like to get this in the model somehow, some way. This bump up.
The stream flow as a fraction of precipitation there is incredibly high. Is that because of inflow from Chicago?
Yes, probably. Yeah.
Yeah, there's.
That's that 3,200 CFS of Lake Michigan water.
Yeah, exactly. And this is
hydrologic cycle that makes no sense.
This is on the Vermilion River, kind of a similar thing.
15 would be a huge number for runoff, wouldn't it?
Yeah, the runoff ratio there would be absurd.
Yeah.
Although it is all pavement.
Yeah, okay. I'm
right.
sorry. The big precipitation change I was thinking of came before our pre-development.
So, why don't we stop there? We've started bringing up a lot of issues on where we need to go. I think that's, I hope you're getting an appreciation for where we were and the work that was done before computers were even around.
Yeah.
But as I told our board recently, I'm getting out while it's easy. It's gonna get a lot tougher as, you know, you've gotten more powerful tools, but then you're expected to do more with them. You know, we're expected to do.
But one of our biggest problems remains that a lot of our best data is in maps like that. And
I'm willing to just not call that good data. That exists.
yeah,
Find some other way.
Yeah.
well, that's the challenge then. What data do we have? So the data we have is LiDAR, it's DEM, it's some stream gauge data, but
So
how do we combine all
we're
that?
looking to populate a stream network, and we're looking to do it based on like where it's important for groundwater interactions. But like there are other ways to populate stream networks that are pretty straightforward. I mean, for surface water stuff, like for the model I built at Iowa, I set a DEM, and from the DEM you can populate a river network. Based off of some flow accumulation threshold.
So
And
Dan,
that's a bad definition for groundwater purposes. But
yeah, Dan has been working on some of those things, and including just filling in, like ditching the NHD and just finding the low flow. Part of the problem is in getting things matched up from our older data because it won't match up. And part of the problem is the DEM having pits in it and filling those in. So Dan's done a lot of work trying to get things burned and what have you, but we still have that problem of not being able to create a monotonically decreasing stream.
yeah, so
We have that
needed
problem.
for running our model too.
Mhm.
We need a monotonic decreasing stream.
Yeah,
Like it won't run if you have it.
Right.
It won't just be ugly. It won't run.
Yeah. Yeah.
So we had, I followed and also helped
So
improve
what
the
exactly is
process
that?
where we were. You take a DEM,
Q7
and sometimes those DEMs were some of the
7 days.
products that were hydrologically enforced.
low
So they burn a
flow.
river network into it.
Oh,
And
the
sometimes they
10-year
were
period
relatively
is
raw.
the lowest
And-
flow, the typical lowest flow.
It's
Over
kind of another
7 days.
process, but at the end, there's a script that somebody developed at
Maybe
Iowa
there's
that you can run, and it'll show you the river profile for every individual stream order stream. So you're looking at every single stream order, one stream you populated, and you look at the river profile for that, and it has an algorithm that you can either go in and manually adjust the elevation right at a point, or you can have it average it out. So it'll raise the point
And
above,
this is defined as the lowest average
it'll raise the
flow that
point
occurs
upstream
for a
and lower
consecutive
point downstream.
7-day period
and
at a
lower
recurrence
the
interval of
artificial
10 years.
so you have a code that does that.
Yeah.
Whoa, okay.
And I'm
Surface
sure
water.
that would be fine sending that.
Yeah, I think that's where Dan got stuck,
Yeah.
is that part in particular. So hopefully Dan will be at the next
So this,
session. 'Cause
for any groundwater modeler, is
You could put a
important
few-
to have.
if you have any slides.
Or, yeah, I can put together slides on the process.
unpublished
Inputs for
Update
that
maps
are
that are floating around that
really
are
specific to
better.
their work.
So, for
So
example,
whereas
So that's why I kept it
Gotcha.
5.
I don't think
So you can each have one.
so for the 20, so from the decade.
everything we do that's
2010
open
to
source. And a lot of it's
2008,
based off of some stuff
The
that was done at
lowest,
Penn
the
State before,
Q7
and that's
was
open source.
based from the.
We have access to that
Drought.
via some method, even if I just have to email my advisor.
Yeah.
like, hey, could you
So
send that?
now
Yeah.
if you redid
Yeah.
the same river, it
Okay.
went dry for 40 days in
And it
2012.
could potentially start with
You
just a
just
shape file.
tend to then drop
Yeah,
to
of a river
0.
network.
Yeah. Okay, cool.
I don't know if they averaged
Well,
the 3 or
work-
I
That
couldn't tell you for sure.
immediately precedes that's done in QGIS.
Maybe that's where we start here then, or pick back up. Because we have something that, I mean, we've used the DEM to come up with our statewide model. We didn't go through this, we like say.
Yeah, I mean, to do this on the scale of a 900 square mile watershed is very different for doing
Yeah.
it on the scale of this.
And that's where we always run into an issue.
Yeah.
Because there's so many,
Just like you
Illinois
can do
River
manually on a small
or
scale, you can't
lake.
manually analyze stuff.
yeah. So how can we get it approximate enough and then what do we need to do whenever we go into a region to refine it?
This is sort of the equivalent of a global model, but
Oh,
Scott liked to quote that thing a lot.
oh,
Oh.
equivalent of a global model.
Oh, well, he calculated recharge rates for the whole Midwest.
Oh, that thing.
Yeah.
Is that a Scott and you phone special?
Well, no, it's Arnold. I don't know. I think it's from Iowa. Where's Arnold from? The lead
Temple,
off.
Texas.
Oh, Texas.
USDA Agricultural Research Service,
There
Temple,
you go.
Texas.
Texas, Iowa, same thing.
Yeah.
Well, we're used to dealing with big things, so we extrapolate.
Yeah, well, they do that way. On a entirely different scale. Do you have any experience, probably not, defining custom rate laws if you're going to workbench?
Oh.
No,
Yeah.
that's my answer, sorry.
Devin, that's a way to clear the room right there.
Yeah, so they're not very clear in the document.